So today I'm just going to briefly record a video going over exam 3, which is going to cover chapters 9 through 12, talking about the oceans and our atmosphere. Starting off with chapter 9, we see that about 70% of the earth is covered in oceans. But we will see that the amount of land and ocean differ between our two hemispheres, our northern and our southern hemispheres. In the northern hemisphere where we live, it's predominantly covered in land and there's very little ocean. But the southern hemisphere is going to be the exact opposite, where it's mostly ocean and there's very little land. We have 5 oceans on Earth. They are the Atlantic, Pacific, Indian, Southern, and Arctic oceans. And 4 out of the 5 have ocean basins. And a basin is just a bowl-shaped depression in the ground. So think about like a cereal bowl and that overall shape. That is what the bottom of the ocean floor would look like in an ocean basin. 4 of our oceans have an ocean basin, but our southern ocean, the one around Antarctica, does not have an ocean basin. And that's because instead of sloping down in the middle of the Southern Ocean, we have the continent of Antarctica. Salinity is the amount of dissolved substances within water. Generally, it's going to be some form of dissolved salt, and we call this salt water. But we want to be able to see how much salt is dissolved inside of our water, so we need to be able to measure it. And to do this, we use the units of percent and parts per million. Salt water is made out of a lot of different salts, but we see that the most abundant salt, or the one most commonly found in salt water, is going to be sodium chloride, or our basic table salt. And all of these salts come from weathering of our continents. Over long periods of geological time, the continents are going to be broken down, and all of those broken down pieces are eventually going to make its way to the ocean, where the pieces are so small they're just going to dissolve. But we're going to see that salinity is not the same worldwide. Instead, salinity, or the amount of salts dissolved inside of our water, is going to vary from place to place. And most of this time, it's going to be dependent on how much fresh water is either being added or removed to the area. So some way that fresh water could be added would be if a river is coming into the area or if glaciers are melting and releasing their fresh water. If we start adding fresh water, that's going to cause the salinity in that area to start decreasing. So think about if I had a 5-gallon bucket that was half full of salt water, and then I fill the rest of the bucket with fresh water. Now the amount of salts is going to decrease, meaning that when I add fresh water, the salinity values are going to decrease. But we can also see that salinity can increase, especially if we are removing the fresh water. If I take a 5-gallon bucket of salt water and I start boiling it, the water that evaporates away is going to be fresh water. That's going to leave all of the remaining liquid water in the bucket with more salt than what it began with. So this is going to be increasing the salinity as we remove the fresh water. And this is going to happen in areas where we have a lot of evaporation occurring, like a really warm area, or it could be in an area where glaciers are forming. But we'll see that when we look at our oceans and we look at the depth from the surface of our oceans all the way down until we meet the seafloor, that the temperature, salinity, and density is going to change. We'll see that at the very top of our oceans, here it's getting a lot of sunlight, so it's going to be very, very warm. But the deeper we go within our oceans, we're getting very little, if any, sunlight. So the deeper we go, the temperature decreases. It gets colder. But we're going to see that overall, the amount that the temperature changes with depth is going to depend on where we are on the planet. In places with low latitudes, like around the equator at 0 degrees, here we're getting a lot of sunlight. So the surface water is going to be really, really warm. And the bottom that's not getting any sunlight is going to be very, very cold. But if we go to our high latitudes, like the North or the South Pole, now we're getting very little sunlight. And the surface is covered with a lot of ice. So therefore, when we're at high latitudes, even our surface waters are going to be cold. Overall, we're going to see that the density of our water, how tightly compacted all of those molecules are, is going to depend on the temperature and the salinity of the water. With temperature, when things are colder, they like to bundle up. So think about sleeping in a really cold room. We're going to ball up and try to preserve our heat. So we see that cold water does the same thing. It contracts and becomes denser. Hot water is going to expand out like we would trying to sleep in a really hot room. So it's going to be less dense. And the density is also going to depend on the salinity because as we increase the salinity, we're adding in more and more dissolved particles. This is going to mean that we have more particles in the same amount of area, also increasing the density. When we look at our oceans, there are going to be three layers that are going to depend on exactly how deep we are. At the very top, or the surface of our oceans, we have the freshwater mix zone. This is where we're going to be receiving a lot of the fresh water, either from like a river or a lake, but we're also going to be getting a lot of fresh water from rain. So the very, very top of our ocean is going to have a lower salinity than the rest because it's having fresh water mixed within it. But if we go from the top to the very bottom, now we're going to see deep water. The deep water that's resting at the very bottom of our oceans is extremely cold. It has a very high salinity and therefore it's extremely dense. So between our surface mix zone and our deep water, in between these, we're going to have our transition zone, where it's just going from warm, low salinity surface water to deep, high salinity, cold water. And depending on, sorry about that. Starting off again, if we're looking at the difference between passive and active continental margins, this is going to depend on the plate tectonics. If the plate tectonics are actively moving around, these are our active continental margins. Here, we're going to find a subduction zone, where we have those two plates that are colliding and one is going to be pushed back into the earth. So we see deep sea trenches around our active continental margins. On the other hand, our passive continental margins, here our plates are not moving. They have been in one position for a long period of time. And this is going to cause them to have very different features. Now, instead of having those deep sea trenches, what we're going to find is a continental shelf, a continental slope, and then a continental rise. With our deep sea or our deep ocean trench, here those two words are pretty interchangeable. We see that these are really deep areas of our oceans. And again, it's coming from subduction. As one plate is being pushed underneath, it's going to pull down the top of that overriding plate. And over time, it's going to make a V shape in the bottom of our oceans, leading to really deep parts of our sea. Those deep ocean trenches, again, are going to be found on our active continental margins. In the middle of our oceans, we're going to find something called an abyssal plain. Abyssal means deep, and plain means flat. So an abyssal plain literally means a very deep, flat area of our oceans. And they form because over time, we're going to have sediment slowly accumulating layer by layer on top of one another. And it's going to lead to very flat layers of our ocean floor. In the middle of these abyssal plains, though, we might have something called a seamount, which just means it's an undersea mountain. And almost all of these are volcanoes. And again, remember that a volcano is still a mountain because a mountain is just a really high area. And then finally, a mid-ocean ridge is where we have an elevated position in our seafloor. This occurs due to divergent boundaries, where we have two plates that are spreading apart from one another. But as they spread, a gap is going to form between them. But we're going to have hot magma coming up from the mantle and filling in the gap between them, creating new seafloor. But this new seafloor just formed from really hot magma. So instead of it being flat, because the middle is so hot, it's going to expand upwards and out, forming a peak shape like a mountain called a mid-ocean ridge. Switching up to chapter 10, we're going to see that winds cause surface currents. So as the wind blows across the surface of our oceans, it's going to literally pull the surface of the water along with it. But our ocean currents are also going to be dependent on the Coriolis effect. And this one is hard to understand. So if you haven't already, I recommend checking out our class YouTube channel and looking at the videos on the Coriolis effect. It's very hard to understand without a good visual. But overall, the Coriolis effect is kind of like an illusion, causing surface currents and wind to look like they're curving, when in reality they're moving in a straight line. And this is because the Earth is spinning out in space. As it spins, our rotation is going to cause not only the wind, but the ocean currents to move in different directions between our northern and southern hemisphere. In our northern hemisphere, we're going to see that it causes both wind and the ocean currents to move towards the right, and it's going to move in a clockwise direction. Whereas the southern hemisphere is going to be the exact opposite. It's going to move to the left, forming a counterclockwise direction. But we're going to see that our ocean currents have a direct impact on what our climate is. Here in Florida, we're surrounded by warm ocean currents, leading us to have warm climates. But if we lived in California, for example, they have cold ocean currents moving through their water, which is going to allow their winters to be cooler than ours. And if you've ever been in the Pacific Ocean in the winter, it's very, very cold. But we can also see something called upwelling developing. Upwelling is when we're going to have really cold, nutrient-dense water that is going to push its way up along a coastline whenever wind is pulling the surface water away. But if we look at our oceans, we're going to see that both our surface and our deep ocean waters is going to be mixing continuously. And this is called the thermohaline circulation. Water around the planet is constantly being moved from one location to another based on its temperature and salinity. Thermo means temperature, and haline means salinity. But we'll see that as we start forming sea ice, we form more glaciers around the North or the South Pole, it's going to have a direct effect on the salinity of the oceans. And this is because when ice forms, it can't incorporate any salts inside of it. Ice will always be pure. So if ice is forming out of salt water, that means that the remaining salt water is going to have a higher salinity over time, which is going to increase the density. An interface is a boundary between two areas where we have a transition zone. And we're going to talk a lot about beaches or coastal areas. And this is an interface between our land, our continents, and our oceans. But we're going to see that a lot of things can affect our shorelines or our beaches. Even things as a single storm can have a massive effect on our shorelines, as well as things like how much sediment or water a river is bringing in, whether sea level is increasing or decreasing, and if humans are building on the shore and exactly what they're building. So a beach is a really good example of an interface. Again, it's just a transition area between our rocky continents and our sediment-filled oceans. So the beach we're generally going to find is a sandy area between our continents and our oceans. We've all likely been to the beach and looked at the waves as they move in. When waves come through and break against a surface, they don't move straight back in and out. Instead, waves always come in at an angle and then they move straight back out. This causes the waves to bend over time. And this is going to lead to something called longshore current or longshore transport, depending on what sources you're reading. They might use one term versus the other. But overall, as these waves keep moving in at an angle and then straight back out, if they do this over time, over repeated waves, that sediment that the waves are carrying is going to be moved along the beach, which is longshore current or longshore transport. So in this case, with my waves coming in at an upward direction, over long periods of time, the sediment is going to be moving along the beach in an upward direction. But depending on whether we're looking at higher amounts of sea level, so if our sea level is rising or if our sea level is falling, we're going to see different types of beaches forming. Some of these might be marine terraces and wave-cut platforms. Both of these happen whenever sea level falls. The water level is going to fall and expose the land that used to be underwater at the beach. Marine terraces look like steps, like a staircase. It's going to have steps to it. Whereas a wave-cut platform is generally going to be a very flat area of solid rock, where the waves have literally cut into the rock over long periods of time. But if we look at places where sediment is being deposited, and we see a lot of this around Florida, we're going to develop things like spits, baymouth bars, and barrier islands. A spit is going to form when sediment is being deposited across a bay. It's going to partially cut off that bay from the ocean water. But a baymouth bar is going to develop once that spit is going from one end of the bay to the other. It's going to connect both sides, completely cutting the bay off from the ocean. But once that baymouth bar has formed, we might see some sea level rise, where the ocean water is going to start covering up parts of that baymouth bar. And this is going to lead to barrier islands, or islands consisting entirely of loose sand. If we were to go to our west coast, however, we might see a different type of beach where we see sea stacks and sea arches. These both are going to look like we just have giant stacks of rock that are just jutting out of the ground at the beach. But we're going to see that a sea arch forms first. Here we're going to get that arch shape that's going to be eroded into a rock by the waves coming in and breaking against the rock over time. But eventually that archway is just going to keep getting taller and taller until eventually it can't support the rock on top of the arch anymore. And it's all simply just going to collapse in. Now we're going to be left with two sea stacks, or two unconnected pieces of rock that are just jutting out of the beach. In the United States, we have two different types of coast. We have emergent coast and submergent coast. An emergent coast is going to occur if our sea level is dropping. It's going to be exposing new land, or it's going to appear as if the land is emerging out of the water. And we find this along the west coast in the US. This is why they have those steep cliffs along California. But in the east coast of the United States, we have the exact opposite. We have submergent coast. Now our coastlines are being submerged with water, meaning the water level is just rising and covering the land or submerging it underwater. And along the east coast, we're continuously losing land along our beaches due to this. So to combat losing our beaches due to the fact that there's submergent coast on the east, we use different engineering techniques to kind of preserve our beaches for longer periods of time. One type is called hard stabilization. This is where we're going to actually just pour concrete and create a structure generally for the water to break against, or at least slow down the energy along our beaches. We have three major types that we use. We have breakwaters, groins, and jetties. But all of these are some form of concrete along the beach. And if we've spent our entire life savings buying a beach house, we don't want to have these ugly concrete structures outside. So we're going to look for an alternative to this hard stabilization. And we're going to go with something called beach nourishment instead. So our hard stabilization is relatively permanent. It's going to remain around for at least a decade. But beach nourishment is very temporary because with beach nourishment, we're going offshore, digging up sand, and then putting it on the beaches. Over time, all of the sand is going to move back out into the water, meaning that within just a few years, we're going to have to repeat this process. It's going to lead to our beaches looking better, but it's going to be a lot more expensive than doing hard stabilization. And the final part of chapter 10 is discussing tides, or how high or low the seawater is. And we're going to have daily tides as well as weekly tides on Earth. And this is because Earth has a moon. And while we can't really feel it, our moon has gravity. It's not enough to suck us off the surface, but it's enough to pull all the water on the Earth. So there are going to be periods of the day and the week where the moon's gravity is going to pull more on the Earth, leading to higher tides. And there are also going to be times where the moon's pull is going to be less. And here we're going to have lower tides. So we have daily high and low tides, sometimes one high and low per day, sometimes two high or low per days. But in addition to these daily tides, we also have weekly tides that go with our lunar calendar. And these are our spring and neap tides. And these are just entire weeks where the moon is either going to have more or less pull on the oceans. So our spring tide is going to occur during our full and our new moons. During these 2 weeks of the month, or weeks of our lunar month, the moon is going to have more pull on our oceans, leading to an entire week of higher tides. But when we're only seeing part of the moon, like a crescent moon, this is going to lead to a neap tide. Now the moon has less pull on our water. So we're going to have low tides for the entire week for our neap tides. And then switching up to chapter 11. This is mostly talking about our weather and climate on the Earth. So we're going to see that weather is what's going on day to day, whether it's going to rain this afternoon, what the high and low temperature is going to be. Weather is constantly changing, hour by hour and day by day. But climate is looking at an area over long periods of time, and climate generally does not change. So for example, the weather today might be 70 and sunny, but the climate in Florida is almost always going to be warm and humid. So the two major components, or the gases found within our air, is going to be predominantly nitrogen, about 78%, and then about 21% oxygen. Inside of our atmosphere, we also have aerosols, and these are just very small solid particles in our air. So if you're familiar with Axe body spray, this is an aerosol spray. You can actually see the solid particles that are being pushed out of the can whenever you're using it. We're also going to see that along our planet, we have a layer of ozone in our atmosphere. And ozone is where we have 3 oxygen molecules bonded together. And it's really important to have in our atmosphere because it's like a sunblock for the Earth. It's going to reflect any incoming harmful UV radiation back out into space so it doesn't hit the surface where we live. But we're going to see that if we start off at the surface of the planet and increase our altitude or go higher and higher in the air, that our air pressure is going to decrease as we increase the altitude. The higher we go, just the less air there will be. But we like to break down our atmosphere into 4 layers. Starting off at the surface of the Earth where we live, the first layer is called the troposphere. Our second layer above that is the stratosphere. Then we have the mesosphere, and then the top or final layer is our thermosphere. And we're going to see that the temperature is going to change as we increase altitude in each layer. So with our troposphere and our mesosphere, we're going to see that the higher we go, the colder it'll be. But in our stratosphere and thermosphere, our temperature is going to increase the higher that we go. If we stick with our troposphere, or the lowermost layer of our atmosphere, we're going to see something called an environmental lapse rate. This means that every 1,000 feet higher we go in altitude, we're going to see that temperature is going to decrease 3.5 degrees. This is going to make it really easy to figure out how cold the atmosphere will be at specific altitudes. But our planet is very unique because it has seasons. And this is because our Earth is not straight up and down in space. Instead, it's tilted. So if we are rotating around the sun, there are going to be periods of time when the northern hemisphere, the top part of our Earth, is going to be tilted away from the sun. In the northern hemisphere, that's our winter, which is why it gets a little colder. But if we go to the opposite side of the year during the summer, now the top part, the northern hemisphere, is tilted towards the sun. It's going to get more sunlight and be warmer. So the reason we have seasons is all due to the tilt of our planet and the way that it rotates around the sun. And we're going to see that there are 3 different locations: the equator, the Tropic of Cancer, and the Tropic of Capricorn. Here, the area of the Earth receiving the most sunlight is going to shift between the seasons. And we're also going to see that the length of daylight is going to change throughout the seasons as well. We generally have longer amounts of time for daylight during our summer when we're tilted towards the sun, and we have shorter daylight hours during our winter when we're tilted away from the sun. But during our spring and autumn seasons, we generally have equal amounts of daylight and darkness. So if we were to look at the sunlight coming in from space as solar radiation or heat and energy, we're going to see that once that radiation starts coming through our atmosphere, getting closer to Earth, some of it is going to be reflected straight back out into space. Some of it is going to hit our atmosphere and just change direction, which is called refraction. And some of it is going to go and actually be absorbed by the surface. So we're going to see that the solar radiation is either going to be reflected, refracted, or absorbed. An albedo is going to be measuring the amount of light that's being reflected off of a surface. And it's going to change based on how light or how dark in color that surface is. So think about having to work outside in the summer, and you get to wear either a white or a black shirt. You're going to be cooler wearing a white t-shirt because the sunlight's going to come and bounce off your shirt. If you were wearing a black t-shirt, because it's darker in color, the sunlight's going to be absorbed, making you warmer. So on our planet, we see that light-colored surfaces, like glaciers, those are going to reflect more light back off. But if we're looking at a darker colored surface, like a forest floor, for example, that would be brown, it's going to have a low albedo, meaning very little light is going to be reflected. And instead, when that light hits the surface, it's going to be absorbed inside of it. But on our planet, We also have what's called the greenhouse gas effect. And these are very specific types of gases that can trap heat in our atmosphere. So think about greenhouse gases being like blankets. I generally like to sleep with a blanket at night. So I want some greenhouse gases in my atmosphere to help keep the surface warm. But if we keep increasing the amount of greenhouse gases in our atmosphere, it would be like continuously adding blankets onto our bed. Now, if I have 50 blankets on my bed, it's going to trap heat close to my body, making me very, very warm. Greenhouse gases are very quickly warming up this Earth's surface in a very similar way. So that we're seeing that globally, the temperature has been increasing the last century due to the amount of greenhouse gases we're putting into the air by burning fossil fuels. So burning these fossil fuels is why carbon dioxide, or why one of the main greenhouse gases, has increased during the last 200 years. We've created manufacturing. We've started using a lot of different materials, and we burn a ton of fossil fuels for our heating and cooling and our home energy, as well as the oil we put in our cars. But some of the things that we can do to help limit our greenhouse gas emissions are things like eating less beef and dairy. We can use less material goods, like buying fewer clothes, not buying single-use items. And we can reduce the amount of water that we're using. But if we wanted to look at the temperature around our planet, we would want to look at something called an isotherm. An isotherm are going to be lines found on weather maps showing you where temperatures are changing. So an isotherm is going to be a line of equal temperature throughout a weather map. But when we look at these weather maps, we're going to see that temperatures are going to shift between water and land. And this is because water has a high specific heat. This means that it takes a lot of energy and therefore a lot of time for water to heat up and to cool off. But land, on the other hand, can heat up and cool off very quickly. And you might have noticed this if you've ever been to the beach on a really hot day. The sand itself might be burning your feet because it is land. It's going to absorb heat very efficiently. But the moment that you step into the water along the beach, it's going to be a lot cooler because it's going to take a lot more energy and time to heat up an ocean in comparison. And this is going to lead to us having different types of temperature control in different locations on a continent. So if we were located around a lot of water, which we are in Florida, this is going to help control our temperature throughout the year. Here, we're always surrounded by warm water. So we have a warm temperature throughout all of the year. But if we lived in like Kansas, for example, where there aren't oceans nearby, it's not going to be able to act like a buffer and control our temperature. If we live in the middle of a continent, we're going to see extreme differences in temperature throughout the year, where we're going to have very hot summers and very, very cold winters. And finally, with chapter 12, this is probably going to be the easiest chapter to understand because it's talking about a lot of things that we see in our day-to-day life. We're going to talk about how water changes states, or how it changes between a solid, liquid, and gas. And there are 6 processes that can do this: freezing, melting, evaporation, condensation, sublimation, and I'm blanking on the 5th, which I almost always do. But with these, we're either adding or removing heat, which might be a little hard to understand at first. So let's think about freezing water. I'm going to fill an ice tray with water and stick it in my freezer. The freezer is going to be removing heat from the water and changing it from a liquid to a solid. If I take that ice out of my freezer, now the heat from my kitchen is going to start being added to the ice, and it's going to melt it and change it from a solid back to a liquid. So each of these steps, we need to look to see whether heat is being added or removed. But when we're looking at our weather, we're going to be concerned with the humidity, or how much water is currently being stored in the air. And if you check the weather before you leave for the day, you might hear, for example, the air has 60% humidity for the day. This is telling us the relative humidity. It's telling us how much water the air is holding in comparison to how much it can hold at a maximum. So if our weatherman is saying we're at 60% humidity, let's say that at maximum, our air can hold 100 pounds of water. At 60% humidity, it's holding 60 pounds of water, or 60% of it. But you might have noticed that when it gets warmer, that the humidity increases. And this is because as the water gets warmer and warmer, it's going to be capable of holding more water inside of it. So we're going to be able to have really hot, humid weather here in Florida because we're separated by all of this water. But in our atmosphere, we also have clouds. And clouds form from condensation nuclei. And this is just a really long word for a very small particle, maybe the tip of my pen. That's going to be a solid particle. And now the water vapor, or that gas form of water in our atmosphere, is going to absorb on top of that. And it's just going to keep getting more and more water vapor until eventually it's going to have enough water vapor to form a cloud. And we name our clouds based on how high or low they are in altitude. So we can have some clouds literally sitting on the surface, and then we can have clouds that are higher up within our atmosphere. But in addition to how high or low they are, we also name our clouds based on their shape. So we might have an altocumulus cloud, for example, telling us the location and altitude and the overall shape of our clouds. So our common types are going to be cirrus clouds, stratus clouds, cumulonimbus clouds, and I'm blanking on the fourth. But we also have fog, which is a very interesting concept to me because fog is just a very, very low-lying cloud, generally a cloud that has come down and is actually sitting on the surface of our planet. But we're going to see very specific times when fog will form. And we're most often going to see it very early in the morning. As the sun starts rising, it's going to start heating up the air in the atmosphere. But after a long night, the ground itself is going to be very cold. So when we have a cold ground and warmer air on top of it, it's going to form fog. And we ended this chapter talking about precipitation and the 9 different forms of precipitation. We might always think about precipitation being some liquid form, but this is not always the case. Sometimes we have solid precipitation as well. But we have 3 types of precipitation where it is liquid throughout, and these are rain, drizzle, and mist. Here, the differences between the 3 are what size are the water droplets. Rain droplets are going to be the largest, drizzle is going to be kind of in the middle, and mist is very, very small or fine water droplets. So think about like a misting fan that you might see at Universal. It's going to be water droplets so small that it's very hard to see, but it's still enough to help moisten our shirts on a hot day. Sleet and glaze, however, we're not going to have liquid precipitation throughout. Instead, it's going to start off as a liquid and end as a solid. With sleet, this is going to be freezing rain. As the water droplet is falling through the air, during its fall, it's going to freeze from a liquid to a solid. But glaze, on the other hand, here our water droplet is going to remain liquid until the moment it hits a solid object at the surface, at which point it's going to immediately freeze. And then finally, if we're looking at hail, hail is only going to form in cumulonimbus clouds. Those clouds that are very tall, going from the surface to very high altitudes. And this is because in those cumulonimbus clouds, they're the ones that produce extreme weather like thunderstorms and tornadoes, as well as hail. And you need a really tall cloud to form hail because hail is a ball of ice that grows layer by layer outward. And this is because along the surface of our Earth, where it's warm, we're going to see an updraft. Air is going to be pushed up to the top of the cloud. And because it's so high in altitude, it's going to be very, very cold. So some of that water is going to freeze into a solid, thereby being heavier, and it's going to fall back to the bottom of the cloud. It might be pushed back up where it's going to freeze again, getting larger, and then fall back down. It'll keep going in these cycles of being pushed up and down until eventually the hail has formed so many layers of ice that it gets too big and too heavy to remain in the cloud, and it's just going to fall from the surface. And generally, this does a lot of damage. If I had a fist size chunk of ice falling, I definitely don't want to be outside. But it's also going to damage the roof of my home as well as the surface of my car. So hail is not something to be messing around with.